In addition to doing a Friedel-Crafts alkylation, one can also do a Friedel-Crafts acylation reaction with an acyl chloride. This is extremely useful because you are able to add a primary carbon to the ring without any shifts. And this is how you get primary carbons to add to rings. What you start out with is an acyl chloride. We have not yet taught you how to make these, so we're going to have to give them to you, but eventually we'll teach you how to make an acyl chloride. And like halogenation and acylation, you start out with aluminum trichloride or aluminum tribromide, depending on what you're starting with. Now, since we're using acyl chlorides, we usually use AlCl3. And as we've seen before, the metal acts as a Lewis acid. It acts as an electron pair acceptor. And in this case, it will accept those electrons from the chlorine. And we'll be able to make our Lewis acid-Lewis base complex again. So let me try and draw this pretty for you. This is the Lewis acid-Lewis base complex, and we have the same problem we've had with halogenation and alkylation. The chlorine here has a positive charge, and so it's going to want to take the electrons from the carbon-chlorine bond to stabilize itself, and it does so. Now, as this occurs, you actually get something kind of cool here. You do get AlCl4. That's not surprising. I'm not going to draw in all my lone pairs on my chlorines, but they are there. You produce what's called an acylation ion. And normally you don't like carbons with positive charges, but this one's got resonance. This one's got a resonance structure, so it tends to help stabilize the situation. You can delocalize that positive charge onto the oxygen. Now, the bottom resonance structure is actually the predominant one because in the bottom resonance structure, everybody has an octet. Now, the positive charge, of course, doesn't want to be on the oxygen, but everybody's got an octet, and that's better than not everybody having an octet. So this bottom one is the major contributor to the resonance, although both are contributing. And you can use either one of these as you show it, adding to benzene. Okay, so again, we're going to have our aromatic ring. We're going to continue to use benzene. And we have our acylation ion. I'm going to use the predominant resonance structure, but you can use the other one. There is nothing wrong with you doing that. But it is electron deficient, and so it's the ring again that acts as the nucleophile, and it will add to the carbonyl carbon, and at that time you break the pi bond if you're using this resonance structure. If you're using the other one, just add it to the carbonyl carbon. And we make our favorite resonance stabilized carbocation intermediate that we've been seeing forever now. Sorry, there is an oxygen up there that I can't seem to draw, but it's there. I wrote a little too high, apparently. Sorry, that one looks so awful. And again, be aware. If you have other groups on the ring, you need to be aware as to whether they are orthopara-directors or meta-directors. If you have positions, like I'm showing here in blue, that are electron donating groups, it will be an orthopara-director. And you would have an enhancement of the resonance because you have an electron donating group adjacent to where the positive charge is in the ring. You would also get one more resonance structure, more than likely if it's a nitrogen or an oxygen, as that nitrogen or oxygen donates its lone pair into the ring, and you delocalize the positive charge onto that nitrogen or oxygen. If, on the other hand, you have an electron withdrawing group, it will be a meta-director, and you would only have the 3 resonance structures that you are shown here. I'll redraw. Alright, so this is what we have, and we also still have the aluminum tetrachloride anion. Tetrachloroaluminate anion. Now, when one of these bonds breaks, the halogen takes the electrons because it is the more electronegative atom. And then it would use its lone pairs, which I did not draw in. It would use those lone pairs to come pick up this proton. This pair of electrons making the carbon-hydrogen bond then will be used to reintroduce the aromaticity into the ring. So that at the end, you will have added this acyl group. So you're able to make a ketone. You can put that in your list of reactions that allows you to make ketones. Now, once you have this ketone, there are some things that you can do with it. You may not want the ketone, and so there are 2 different types of reactions you can do with it. You can do what's called a Clemmensen reduction, or you can do a Wolff-Kishner reduction. It depends on what other groups may or may not be present, but both of these will be able to reduce the carbon-oxygen double bond to a CH2 group. I'm just going to write the conditions down. I'm not going to take time to do these mechanisms at this point. They are discussed a little later, and we'll show those in later slides. But I just want you to be aware of the conditions that allow you to reduce the carbonyl group. So, Wolff-Kishner conditions, you can do this with either zinc or mercury, and you would use HCl. And it doesn't do anything to the length of the carbon chain, leaves that entirely alone, but you can convert this to an alkyl group. And this is really cool because you might have wanted to add a primary carbon to this ring without doing a rearrangement, and this is how you get this to occur. You also could use Wolff-Kishner conditions and do the same thing. Wolff-Kishner involves a molecule called hydrazine. This is hydrazine. You use a little bit of hydroxide, and you do this typically in a high boiling solvent like triethylene glycol. And you heat it up a lot. Now, there are advantages to using one over the other at different times. If you notice, the Clemmensen conditions are in acid, and the Wolff-Kishner conditions are in base. So if you have acid or base-sensitive groups, you may want to use one over the other. Be aware that this Clemmensen condition, this one right here, it could be an issue if you have a nitro group, an NO2 group. It will take the NO2 group and convert it to an NH2 group. It doesn't just reduce carbon-oxygen double bonds, it also reduces nitrogen-oxygen double bonds. So if you had a nitro group on there and you wanted to leave it alone, you might want to use the conditions shown down here below. Okay, the Clemmensen conditions would convert it to an NH2 group. but Wolff-Kishner would leave it alone. So be aware of those things. You might also have some other groups that are base sensitive. So watch what you're doing. Just be aware of what other groups are on your ring so that you know what you need to do and when to do it.